This is the second video in section 1.6, the second derivative, wherein we will actually talk about the second derivative. So the second derivative of f of x is just the derivative of the derivative. So in other words, it's f prime prime. And the notation that we use for the second derivative is f with two primes, or we'd say f double prime of x. So that's the second derivative, the derivative of the first derivative. And by definition, if the second derivative is the derivative of the first derivative, well, I can just use the limit definition of the derivative and have f double prime of x is the limit as h goes to 0 of f prime of x plus h minus f prime of x all over h. So that is exactly what it means to be the derivative of the first derivative. Now, the second derivative of f will tell us how the rate of change, which is f prime of f, is changing. So it's the rate of change of the rate of change, basically. So let's see what that means graphically. Okay, so a function that looks like this is something that's called concave up. So it sort of looks like a cup that's facing upwards, concave up. That's what it looks like. And notice what happens, oh, this is f of x. So notice what happens if I start drawing little tangent lines as I move from left to right. On the far left, I have a pretty big negative slope. Then I have a less negative slope. I have sort of a zero slope. I have a small positive slope, bigger positive slope. So as we move from left to right, the slopes of the tangent lines are getting bigger. They're going from very negative to 0 to small positive to big positive. So slopes of the tangent lines are increasing as I move from left to right. So that's sort of the definition of what it means to be concave up. Now notice that the opposite is what we call, oh, I forgot to write it, concave down. So a function that's sort of facing down is what is something called concave down. And notice if I draw my slopes of tangent lines going from left to right, I start with something that's big and positive, less positive, gets close to 0, 0, then it starts small negative and then gets more negative. So as I move from left to right, the slopes of my tangent lines are decreasing. They're getting smaller as I move from left to right. So that's what it means to be concave down. Now let's put that together with what we know about the second derivative, namely that it's the derivative of the first derivative, and we get the following theorem. Let's suppose that we have a differentiable function on some interval from a to b, then f is concave up on that interval if and only if f prime is increasing on that interval. So we just saw f is concave up if the slopes of the tangent lines are increasing. Well, slope of tangent line is derivative, so that means derivative is increasing on that interval. But what does it mean for the derivative to be increasing? That means that the derivative of the derivative should be greater than 0. In other words, f double prime is greater than 0. So all of those three are equivalent statements. F is concave up if and only if f prime is increasing, if and only if f double prime is greater than 0. And we can do the same thing for concave down. We'll say f is concave down on the interval AB if and only if, remember from the previous page we saw the slopes of tangent lines were decreasing. Well, that means f prime is decreasing on AB. And that's true if and only if the derivative of the derivative is negative. In other words, if and only if f double prime is less than 0 on the interval AB. So concave down, derivative decreasing, f double prime less than 0 are all equivalent statements. Thus, the sign of f double prime tells us about the concavity of our function f of x. In other words, it tells us whether f of x is concave up or concave down.